To understand how a self-driving car operates, we have to look at the traditional modular architecture. In this setup, a vehicle's perception system is separated from its planning system. Engineers write hundreds of thousands of lines of explicit instructions using C++, a high-level programming language, to tell the car exactly how to behave. This creates a strict if-then logic funnel. The vehicle's cameras identify an object, like a stop sign or a pedestrian. Then the car's computer consults a library of explicit engineering rules to determine its physical reaction. If the object is a red octagon, then apply the brakes. That logic works well in highly controlled environments, but real-world driving is defined by chaos. Engineers call unpredictable rare events edge cases, and they make up a long tail of roadway entropy that is difficult to fully anticipate. Imagine a cyclist suddenly swerving to avoid a pothole, while a delivery truck obscures the crosswalk. When encountering this chaotic combination, the car searches its database for an explicit rule. If it cannot find one, the system hesitates or freezes completely. The physical world contains a near infinite number of these variables. Trying to write enough code to cover every conceivable combination of weather, lighting, pedestrian behavior, and road condition is a mathematical impossibility. To build a vehicle capable of navigating any environment, engineers moved away from human-written rules. They needed an architecture that does not rely on strict logic, but instead learns to adapt to chaos on its own. Tesla's full self-driving version 12 sweeps away those hundreds of thousands of lines of C++ code. In their place, it uses a single end-to-end neural network. A neural network is a computing system inspired by the human brain that learns to recognize patterns directly from large amounts of data. This is what Tesla calls a photon-to-control architecture. Raw video input from the vehicle's 8 cameras funnels directly into a single AI model, which translates those pixels into vehicle control commands, like adjusting the steering angle or applying brake pressure. Instead of following programmed rules on what to avoid, the network learns the actual mechanics of driving. It achieves this by imitating millions of video clips of human drivers navigating real roads. The result is a driving style that mirrors human intuition. Rather than executing binary stops, the system learns subtle behaviors, like gently creeping forward at a blind intersection to signal intent, or smoothly adjusting into lane position when passing a large semi-truck. Processing this density of complex data requires a high-performance computer built directly into the car. Tesla's full self-driving computer, for instance, can process up to 2,300 frames per second, a massive jump in image processing speed that allows these neural networks to output driving commands with near zero latency. Connecting camera pixels directly to steering commands allows the vehicle to navigate by observation. The car no longer waits for an engineer to define a specific scenario. It relies on its internal weights to determine the safest path forward. An end-to-end neural network is useless without information to learn from. To train a model to handle the entropy of the real world, you need petabytes of high-fidelity real-world data. This is Tesla's data engine, a continuous feedback loop utilizing the millions of customer vehicles currently driving on roads around the world as a distributed sensor network. Every time a customer drives, the vehicle operates in shadow mode. The onboard computer runs the self-driving software in the background, comparing the AI's intended actions against the human driver's actual inputs. When a driver intervenes, the car flags that discrepancy and sends the video clip back to the servers. To process these clips, Tesla employs multi-trip reconstruction. By merging overlapping video clips from multiple vehicles passing through the exact same location, the system automatically builds a high-definition 3D ground truth of complex intersections. To digest this information, Tesla built the Dojo supercomputer. Dojo's purpose is to process massive 4D video tensors, multi-dimensional arrays of data capturing 3D space as it changes over time, allowing engineers to rapidly retrain the neural network and push updates back to the fleet. For the rarest driving scenarios, Tesla uses a neural world simulator. This AI-generated twin environment creates infinite photorealistic variations of extreme edge cases, acting as a stress testing ground for the driving model. The algorithm alone does not solve autonomous driving. The barrier to entry is this closed-loop data pipeline, collecting real-world mistakes and using them to constantly evolve the software. With version 13, the system introduces a world model. Instead of merely reacting to the present moment, the AI simulates the environment, projecting plausible future paths for every pedestrian, cyclist, and vehicle over the next several seconds, and adjusting its own trajectory proactively. This predictive approach stands in contrast to competitors. Many other autonomous platforms rely on expensive, pre-mapped routes paired with LiDAR, a remote sensing method that uses pulsed lasers to measure precise physical distances. If a city alters a traffic pattern or a construction crew shifts a lane, map-dependent systems can struggle. Tesla's vision-only system reads the physical environment like a human driver, allowing it to navigate chaotic urban areas using generalized intelligence rather than static high-definition maps. Because the system learns from visual data rather than strict automotive rules, the underlying neural architecture is not bound to a car. It is designed to interpret and interact with the physical world universally. The same AI engine and world simulator used for the vehicles are being ported directly into Tesla's humanoid robot, Optimus. Navigating an intersection and walking across a factory floor share the same underlying requirement: real-time spatial reasoning. By applying the same world simulator and neural network architecture to humanoid robots, Tesla is testing whether an AI trained on the road can successfully interact with the rest of the physical world.